Alrighty, so here we go. Momentum 2. Alright, in this one we are going to look a little bit more in depth into conservation of momentum. Conservation of momentum and Newton's second law. Actually, Newton's second and third laws. We are going to look at not straight returning, bouncing. So in the last video I showed you, a particle coming along, hitting a wall, bouncing straight back off. This time we're going to look at particles that aren't quite so straightforward. So they'll be coming in kind of like this scenario. All right, but what I will do is rotate it. You'll see why in a minute. But to start with, conservation of momentum in terms of Newton's second and thirds. Righto, so last video, F equals ma is mv on t, or m delta v on t, which was the change of momentum over some sort of time. Vector, 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 vector. Alright, so now what we're going to look at is how this relates to Newton's third law. So we know that for every action there's an equal and opposite reaction. For every particle that collides with an object, that object also collides with the particle. So now we can look at really not simple, but we can look at reasonably straightforward collisions of two objects. So what we're going to look at now is two things: particle 1, object 1, and object 2. Alright, so if the force on mass 1 is its mass times by its change of velocity over time, so its change of momentum, we can kind of say that the change of momentum of particle 1, so force on particle 1 is its change of momentum over the time that the impact took. We can look at the force on the second particle as the change of its momentum, vector, 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 vector. Alright, its change of momentum over a certain amount of time. Now, I've written T for both because it's the same bloody impact. So of course the time amount is going to be the same. You're not going to have a tennis ball hitting the ground for 0.2 seconds, but the ground hitting the tennis ball for 0.1 seconds because it's bigger or something. It just doesn't happen like that. So now we can go back to here, F1 minus F2 vector. And I'm going to change colours just to hopefully make this stand out a little bit more. Here we go. So now I'm going to grab all of this from over here and replace these two terms. So in this case here, remember the first force is equal and opposite. That's why I've got the negative there, because it's the same size, opposite direction. Alright, change of momentum 1, change of momentum 2. So F1, change of momentum 1 over t, is equal to negative change of momentum of object 2 over t. Alright, so now we can say, well, we're dividing both sides by t. T, as we said over here before, is the same. So these two cancel each other out. Therefore, change of momentum of the first object is equal and opposite to the change of momentum of the second, or change of momentum 1 plus change of momentum 2 is nothing. Okay, so this is kind of weird, but what it basically means is that if we add up all of the bits of change in momentum for all of the particles that are involved in this interaction, this collision, we can have a cajillion particles, delta p1, delta p2, delta p cajillion, and adding up all their bits of change of momentum is going to equal 0. So these forces were the forces of interaction. They're the internal forces. We're not talking about external ones like I don't know, gravity and change of momentum from photons of light and weird shit like that. What we're talking about is the change of momentum of the first particle plus the second plus the third plus the fourth plus the fifth, etc., etc., is equal to nothing. So therefore we can say that the sum of all of the change in momentums is 0, or momentum is conserved. Alright, so if you add up all of the changes and they cancel each other out, that basically means that there's no change in momentum. If there's no change in momentum, momentum is conserved. And there's no exterior, or I should have written external forces. Okay, so when there's no external forces, there are no changes in momentum. Alright, so we try to simulate them, ice intersections, ice skating, all that sort of stuff, just to ignore the effect of friction, just like we were ignoring the effect of wind resistance back 6 weeks ago with the projectile, or a couple of months ago with the projectiles. Alright, so F equals ma, m delta v over t. The m delta v is change in momentum, so then we can relate Newton's second law and his third law, sort of smush them together with some substitutions from back over here, and we find that they all kind of balance each other, they all cancel out, so momentum is in fact conserved.